You are standing on the only known object in the universe that has ever produced a philosopher. Not the only object that has produced carbon. Not the only object that has sustained chemistry. The only object that produced a creature so disoriented by its own consciousness that it spends its entire life trying to understand what consciousness is. A creature that looks at stars and feels something it cannot name. A creature that writes music about dying. A creature that picks up a glass of water and, given enough context, begins to cry. This planet, this specific, unlikely, almost didn't happen planet, the only place in all of the observable universe, a universe containing 2 trillion galaxies, each with hundreds of billions of stars, where we have evidence that something looked at the sky and asked, "What am I?" The answer is not what you expect. It is older than you expect. It is more violent than you expect. It is at every critical moment more fragile than you have ever allowed yourself to believe. And it is by the narrowest margin, through a sequence of catastrophes that should have ended it at least a dozen separate times, the most improbable narrative in the known universe. This is how the Earth was made. This is how life began. This is how you got here. And why, at every step of the way, you almost didn't. If you have ever looked at the sky and felt something you couldn't name, subscribe and hit the bell, because what you are about to understand will make you feel it again. And this time, you'll know exactly what it is. This is a channel about what science reveals about being human. Not about data, about what the data means at 3 in the morning, when no one is watching and you let yourself actually feel the weight of the world you live in. If that is the kind of understanding you are looking for, this is where it lives. It begins not with a bang, it begins with dust. And the dust begins with death. The universe is not generous by nature. It does not distribute planets to passing solar systems as a matter of routine. It does not assemble worlds from raw materials and leave them waiting for biology to arrive. Everything this planet is made of: the iron at its core, the oxygen in your lungs, the calcium in your teeth, the carbon in every cell in your body, was forged inside stars that lived and died before the sun existed. Stars so ancient that they burned out and exploded billions of years before the first atom of the Earth was assembled. Stars whose names we do not know because they burned out before there was anything alive to name them. Take a breath. You just inhaled oxygen that was synthesized in the nuclear furnace of a dying star. The nitrogen in that same breath was forged in a different star, in a different explosion, possibly in a different arm of the Milky Way. The iron that your blood uses to carry that oxygen to your brain was manufactured in the final seconds of a massive star's life, in the catastrophic collapse and detonation we call a supernova, an explosion so energetic that it briefly outshines every other star in the galaxy combined. You are made of the ashes of events that happened before the sun was born. You are not a new thing. You are a very recent arrangement of very ancient matter. And the story of how that matter was arranged across 4.54 billion years, through a chain of disasters that should have ended the story every time, is the most unlikely narrative the universe has ever produced. The story starts in a molecular cloud. Not a cloud like the ones you see from an airplane window. A molecular cloud is a region of interstellar space, predominantly hydrogen and helium, containing the ash of dead stars, carbon, nitrogen, sulfur, silicon, iron, calcium, phosphorus. Every element heavier than hydrogen and helium. Each one synthesized inside a star that no longer exists, scattered by the violence of that star's death across hundreds of light years of dark. A molecular cloud can span 200 light years from edge to edge, so vast that a beam of light traveling at 186,000 miles per second would take 2 centuries to cross it. And this cloud, for the most part, does nothing. It drifts, it cools. It carries the chemical legacy of billions of years of stellar life and death through the dark, patient and cold, waiting for something to disturb it. About 4.6 billion years ago, something did. A massive star in the general neighborhood of where our solar system now sits reached the end of its life. When the nuclear fuel in a massive star runs out, the star's core collapses inward in a fraction of a second, a volume the size of Earth compressing to the size of a city. The rebound detonates the star's outer layers in a supernova explosion that releases, in those few seconds, as much energy as the Sun will produce over its entire 10 billion year lifetime. A wall of compressed gas and radiation propagated outward at tens of thousands of miles per second. When it reached our molecular cloud, the cloud rippled. Compressed. In certain regions, the gas and dust grew suddenly dense enough for a force that had been failing to matter to finally take hold. Gravity. Gravity, once it takes hold, does not let go. The cloud began to fall inward. Slowly over millions of years, the movement barely perceptible even on geological timescales. But as it contracted, it spun faster because the cloud had been rotating slightly when the shockwave hit it. And rotation accelerates as the mass moves inward, exactly as a spinning figure skater accelerates when she pulls her arms in toward her body. The center of the collapsing cloud grew denser, hotter. 1,000,000 degrees, 10 million, 100 million. And then at the threshold where hydrogen nuclei moving fast enough overcome the electromagnetic force that repels them and fuse into helium, the center ignited. The Sun was born. What remained, the material that had been orbiting the newly formed Sun in a rapidly spinning disk, was now exposed, a flat plane of gas and dust, rotating around a star cooling at its outer edges, organizing. The protoplanetary disk, the cradle of the Earth. And what it contained at this moment was a vast quantity of essentially nothing. Dust grains smaller than the period at the end of this sentence. Each one a chemical capsule from a dead star, each one drifting in the thin, cold disk, subject to no force sufficient on its own to pull it together with its neighbors. Nothing so far has happened that should produce a planet. The mechanism that started the process of planet building was discovered not by a planetary scientist, not in a laboratory, not through a theoretical model. It was discovered in 2003 by an astronaut who was bored. Don Pettit was a NASA flight engineer aboard the International Space Station in 2003, and in a spare moment he filled a plastic bag with ordinary table salt, sealed it, and shook it. In zero gravity, the crystals should have scattered randomly. Instead, when he shook the bag and stopped, the crystals reached for each other. Clumps formed almost immediately. Pettit filmed it and sent the footage to a colleague named Stanley Love. Love watched it and said, "Don, that is neat. Actually, you've just solved a very old problem in planet formation. When dust particles in zero gravity rub against each other, they exchange electrons. The same electrostatic charge that causes a balloon rubbed on your hair to stick to a wall causes, in the cold, thin disk of the early solar system, dust grains to attract each other across small distances. In the protoplanetary disk, where countless particles were perpetually colliding and separating and drifting past each other, this charge built up everywhere at once. Grains reached for their neighbors and held on. Small clumps formed. The clumps reached for each other. Larger clumps formed, and so on over millions of years. From dust grains to pebbles, from pebbles to boulders, from boulders to objects a kilometer across. And at approximately half a mile in diameter, something changes entirely. A rocky body half a mile across has enough mass that its gravitational field reaches noticeably outward into the disk. It begins to pull in material, and the more it pulls in, the larger it becomes. The larger it becomes, the stronger its pull. The stronger the pull, the more material it gathers. Faster and faster, runaway accretion. Roughly 20 protoplanetary bodies formed in the inner solar system. Within the first 30 million years of the solar system's existence, 20 worlds circling the young sun, each with its own gravity, each in its own orbit, each growing, each inevitably being drawn toward the others. The star that died for you before there was an Earth. There was a star that has no name in any human language. It burned for 20 million years, fusing hydrogen to helium in its core, then helium to carbon, carbon, to neon, neon, to silicon, silicon to iron. Each fusion reaction releasing energy, each one sustaining the star against the gravitational collapse trying to crush it. When it reached iron, the production line stopped. Iron cannot be fused to release energy. Within days, the star's core collapsed. In less than a second, a volume of space the size of the Earth compressed to the size of a city. In the explosion that followed, every element heavier than iron, gold, platinum, uranium was forged in the extreme conditions of the detonation itself. And then the star's remains were scattered across hundreds of light-years of interstellar space. The star did not know this would happen. The star did not know anything. But its death seeded the molecular cloud that would 4.6 billion years later be compressed by another supernova shockwave collapse into a disk, and eventually assemble itself into a planet and an ocean and a bacterium, and a fish and a mammal and a creature that would sit down and try to understand what it was made of. The star never knew, but here we are nonetheless reading this with eyes built from its ashes. Not A, but B. Not the sun formed and the planets accumulated from leftover material, but the sun formed from stellar death and the planets accumulated from stellar ash. And you are a sculpture made from the remains of something that burned out billions of years before you existed. The 20 protoplanets were circling the sun, growing. But gravity does not only build, it also hurls. And the same force that pulled the Earth together was about to begin a campaign of destruction so complete that it would reduce 20 worlds to 4. The question is, what was built in the process? And the answer is the only reason you can breathe. Everything the Earth needed to sustain life had to be beaten into it. That is not metaphor. That is the mechanism. The formation of a rocky planet requires an uninterrupted sequence of collisions. The technical term is accretion. What it means in practice is that for 200 million years, the growing Earth was subjected to impacts of a frequency and scale that dissolve every reference point we have for describing violence. Every few weeks in the early period, an object the size of a city struck the growing proto-Earth and released energy equivalent to thousands of nuclear weapons simultaneously. Every few million years, something larger arrived and released energy equivalent to the entire nuclear arsenal of the modern world, detonated all at once, many thousands of times over. For 200 million years, the surface was not solid. There was no surface. The Earth was an ocean of liquid rock magma from pole to equator, perpetually disturbed by the next impactor arriving from the disk. The Earth was not born, it was hammered. But here is what the hammering accomplished that nothing else could have. As the planet grew larger from the continuous bombardment, the heat kept the interior molten all the way through down to the core. A molten planet subjected to gravity does what all liquids do. When given enough time, it separates by density. The heavy materials sink, the light materials rise. Iron is heavy. The young Earth had iron in enormous quantities, iron hammered in by impactors. Iron present in the original dust grains of the protoplanetary disk. Molten iron freed from the solid rock matrix by the heat of formation began to descend, not all at once over millions of years in a slow gravitationally driven rain. Liquid metal falling through liquid rock gathering in the deep, hundreds and then thousands of miles down, compressing under the weight above, eventually forming the Earth's outer core, an ocean of liquid iron about 400 miles thick, surrounding a solid inner core compressed to solidity by sheer weight. The liquid outer core convects. As the Earth rotates, this vast ocean of liquid metal moves in organized patterns, and a moving conductor in a magnetic field generates a magnetic field. The Earth's liquid iron outer core, convecting in a rotating planet, generates a magnetic dynamo. And the dynamo generates the magnetosphere, an invisible sphere of magnetic force extending 40,000 miles into space in every direction, deflecting the charged particles of the solar wind before they can reach the atmosphere. That sphere is the reason you are alive. The solar wind is a continuous stream of charged particles, protons, electrons, alpha particles flowing from the sun at 1,000,000 miles per hour. These particles are energetic enough to strip the molecules of an atmosphere away into space one by one, molecule by molecule, century after century, until there is nothing left. We do not have to imagine what this looks like. We can look at it through a telescope. Mars formed in the same protoplanetary disk as the Earth from the same materials at roughly the same time. For the first 500 million years of its existence, Mars had a magnetic field, a dense atmosphere and liquid water on its surface. The minerals on its surface today, clay minerals, sulfates, carbonates, only form in the presence of standing water. Mars was wet. Mars was for 500 million years arguably habitable. And then Mars's iron core cooled and stopped convecting. The dynamo collapsed, the magnetic field decayed. The solar wind stripped away most of the atmosphere. The water evaporated, the surface dried. Today, the Martian surface temperature averages -80 degrees Fahrenheit. The radiation environment would give an unprotected human a lethal dose in minutes. Mars is what Earth would have become without the iron core. Mars is Earth's warning, the cautionary twin built into our solar system to show what happens when the armor fails. The Earth's iron core generated the magnetic field. The magnetic field deflected the solar wind. The atmosphere was preserved. This is not a story about luck. This is a story about mechanism. 200 million years of bombardment generated enough heat to melt the planet, which allowed the iron to differentiate to the center, which allowed the dynamo to form, which protected everything that came after. The violence was the shield. The catastrophe was the condition for survival. But the shield by itself was not enough. The Earth, protected from the solar wind, was still a lifeless desert. No water, not a single molecule of liquid water anywhere on the planet, because the inner solar system was bone dry during planet formation. The water was out beyond the asteroid belt, frozen in rocks that had been accumulating ice for millions of years in the cold beyond the frost line. And between those icy bodies and the dry inner planets stood the most gravitationally dominant object in the solar system after the Sun. Jupiter was about to rearrange everything. The world before water, stand on the early Earth, and the ground beneath your feet would be black volcanic rock, still warm, cracked into continent-sized plates by the slow convection of the magma beneath. The sky above you would be orange-brown, thick with carbon dioxide and methane and sulfur dioxide. A sky that would kill you in minutes, a sky with no ozone layer to stop the full ultraviolet output of the young sun from reaching the surface. There is no ocean, there is no river, there is no rain. There is no sound except the wind across black rock and the distant rumble of a planet still settling into its final form. You are standing on a world that has all the raw materials for life. The right distance from the sun, the right magnetic field, the right mass, and absolutely none of the ingredients. It is a promise not yet kept. Somewhere beyond the faint glow of Jupiter's disk, barely visible in the sky, frozen water is waiting in ancient rock for a gravitational nudge that hasn't happened yet. Waiting to fall. The Earth was dry. It had its armor, but armor alone doesn't sustain life. Something had to deliver the water, and Jupiter, through a mechanism no one intended, was about to send it. What happened next was simultaneously the most destructive period in Earth's history and the origin of every ocean, every river, every raindrop that has ever fallen. And before the water finished arriving, something else was already on its way, something that would end the world as it existed and make everything we know today possible. Jupiter has no interest in the welfare of the Earth. Jupiter does not have interests. Jupiter is a ball of gas and ice and rock with a mass 2.5 times greater than all the other planets in the solar system combined, and it exerts its gravitational influence on everything in its vicinity with the complete indifference of a force of nature. It does not intend consequences, it simply acts. Approximately 4 billion years ago, the exact timing is still debated, with some research suggesting the major phase may have begun as early as 4.48 billion years ago. Jupiter and Saturn were settling into their current orbital positions after a period of migration that had already substantially reorganized the solar system's architecture. As they moved, their combined gravitational resonance propagated through the asteroid belt in waves. not metaphorically but as literal gravitational resonance frequencies that matched the orbital periods of asteroids at certain distances from the Sun. Asteroids whose orbits fell into these resonance zones were perturbed. Their circular orbits became ellipses, their ellipses stretched, and eventually for enough of them over long enough periods, those ellipses intersected the orbit of the Earth. The result was a period of intense asteroid bombardment of the inner planets that we call the Late Heavy Bombardment. Though the term is increasingly contested, some researchers now believe the bombardment was not a discrete spike, but a gradual decline from the initial chaos of solar system formation, with the timing we previously attributed to it actually being an artifact of where the Apollo astronauts collected their lunar samples. But whatever the precise character of the bombardment, its consequences were not contested. Enormous numbers of asteroids, many of them from the outer belt, where water, ice had been incorporated into the rock during the disk's formation, arrived at the Earth in a sustained barrage that lasted tens of millions of years, and each one brought water. Not much water per impact. A city block-sized asteroid perhaps 100 meters across. Delivered on impact, perhaps a few million gallons of water, the contents of a modest reservoir, an afternoon's flow of a minor river. But there were not a few asteroids. The asteroid belt contains hundreds of thousands of objects large enough to have delivered meaningful quantities of water, and in the early solar system, many more existed. Over tens of millions of years of bombardment, impact by impact, drop by drop, the water accumulated. The evidence for this is not abstract. The evidence sits in laboratories in carefully preserved meteorites and in tiny crystals of ancient rock. In January 2000, a meteorite entered Earth's atmosphere over western Canada and landed, shattering into pieces on the frozen surface of Tagish Lake in British Columbia. Within days, scientists were on the ice, carefully extracting fragments that had been cold, preserved in the frozen lake pristine, uncontaminated by Earth's environment in a way that meteorites landing on dry ground almost never are. Analysis of this meteorite, one of the most important specimens ever recovered, revealed that it was approximately 20% water by weight, not as liquid, obviously, as water molecules locked inside clay minerals, trapped in the matrix of the rock like letters pressed into wet cement, preserved there since the asteroid formed 4.6 billion years ago, roughly the age of the solar system itself. In September 2023, a capsule dropped through the Utah sky and was retrieved by NASA scientists. It contained 120 grams, roughly the weight of a bar of soap, of material collected directly from the surface of asteroid Bennu by the OSIRIS-REx mission. Over the next 2 years, as laboratories analyzed that material with the most sensitive instruments available, they found things no one had expected to find in such abundance. 14 amino acids, the molecular building blocks of every protein in every living thing on Earth. 5 nucleobases, the molecular letters of the genetic code, the specific chemical alphabet in which DNA and RNA write the instructions for every organism that has ever lived. Phosphates, complex organics, and water. Bennu is 4.6 billion years old. It has never been warm. It has never had a biology. It has never in all of its history been anywhere near a living thing. And it was carrying locked in its ancient rock the complete molecular toolkit for life. The asteroids were not just delivering water. They were delivering the ingredients. The evidence for the timing came from a geologist named Stephen Modzis at the University of Colorado, working in a remote area of Western Australia, one of the few places on Earth where rocks old enough to preserve the record of the earliest Hadean eon are exposed at the surface. Modzis extracted from ancient volcanic rock tiny crystals called zircons. Zircons are common minerals, but they are also essentially indestructible, and they record in their oxygen isotope ratios the conditions under which they formed. The zircons Modzis analyzed dated to 4.4 billion years ago, some of the oldest known minerals on Earth, and their isotopic signature could only have been produced in the presence of liquid water. The oceans began forming within 150 million years of the Earth's creation, on a 12-hour clock representing Earth's entire history within 25 minutes of noon. The asteroids had delivered the water, the oceans formed. The first ocean, the first rain on Earth was not like any rain that has fallen since. It began as steam. The early atmosphere was too hot in the first hundreds of millions of years for water to remain liquid at the surface. But as the planet cooled, as the pace of bombardment slowed, and the heat, generated by each impact, had more time to radiate away, the temperature at the surface crossed a threshold. And when it did, the steam condensed. And for the first time in the history of this planet, it rained. Not briefly, not lightly. It rained for perhaps 100,000 years, as the enormous amount of water vapor in the early atmosphere precipitated out into the first ocean. The ocean was not blue. It was green-brown, saturated with dissolved iron from the volcanic sea floor, rich in minerals from the basalt that formed its bottom, lapping against shores of black volcanic rock under a sky still reddish-orange with carbon dioxide and methane. There was no blue sky, no white clouds, no sand on the beaches because there were no beaches, only black rock, meeting green water at the edge of a shallow sea. But it was water, liquid water covering the surface of a planet held there by gravity, warmed by the sun, sustaining the chemistry that would need perhaps another 500 million years to try something extraordinary. The stage was set, the chemistry was in place. No one was watching, nothing knew it had happened. But it had happened. From this point forward, from the moment the first ocean formed, the story is no longer about geology in isolation. It is about the intersection of geology and chemistry. The ocean was a medium, a solvent, a vast, patient, mineral-rich solution in which the molecules delivered by the asteroids, the amino acids, the nucleobases, the organic compounds found preserved in rocks like Bennu, could encounter each other, combine, break apart, recombine. In tidal pools along the volcanic coast, the chemistry concentrated and dried and re-wetted in cycles driven by the enormous early tides. In deep-sea hydrothermal vents, chemical gradients drove reactions that would otherwise have required the input of energy from sunlight. In crater lakes formed by the continuing asteroid impacts, the shocked and heated rock created unusual mineral environments that catalyzed reactions that would have been too slow in the open ocean. The chemistry was running. The question was whether somewhere in the vast experimental space of a planet-sized chemistry set running for hundreds of millions of years, any particular combination of molecules would happen upon something with a property that nothing in the universe, so far as we know, had ever managed before. The property of copying itself. The origin of life, the moment when non-living chemistry crossed the threshold into something that could replicate and evolve, is the most scientifically contested and philosophically consequential question in all of biology. We do not know exactly how it happened or where or when, but we know it did, and the oldest witnesses to its having happened are still alive today, living in a remote bay on the west coast of Australia, sitting in shallow water and doing what they have been doing for 3.5 billion years, quietly and without acknowledgement, building the atmosphere that you are currently breathing. There is a bay on the western coast of Australia called Shark Bay. The water is too salty for most of the grazing organisms that would otherwise eat the bacterial mats growing on the seafloor there. Because of that saltiness, because of that specific local hydrological accident, something survives in Shark Bay that has been living on this planet for 3.5 billion years. Something that exists in only 2 locations in the modern world. Something that over the course of 1 billion years of patient unconscious, invisible work changed the chemistry of an entire planet's atmosphere and, in doing so, made every complex organism that has ever lived here possible. They are called stromatolites. They are not impressive to look at. Dome-shaped mounds of layered rock and living bacteria rising from the seafloor like small irregular boulders. Tourists are sometimes disappointed. They do not move. They do not react. They sit in the water and do what they have been doing for 3.5 billion years. A visitor to Shark Bay would find them easy to miss. They are the oldest living things on Earth. They were present on this planet before there were eyes to see them. They built the air you breathe, and they did it without knowing they were doing anything at all. When geologist Martin van Kranendonk found fossil stromatolites in the Pilbara, organisms structurally indistinguishable from those living in Shark Bay today, preserved in rock 3.5 billion years old, he described the experience of walking across that ancient landscape as being transported back through time. The same structures, the same scale, the same patient geometry of bacterial layers accumulated over millennia, pressed and mineralized into rock, but otherwise unchanged. He said it gave him goosebumps. It should. These fossil stromatolites are 15 times older than the dinosaurs. They predate the evolution of the eukaryotic cell, the more complex cell type that forms the basis of every organism you can see with the naked eye, by approximately 2 billion years. For 1 billion years after life first appeared on Earth, the only living things on this planet were bacteria and the organisms most closely related to bacteria. For 1 billion years, the Earth belonged entirely to microbes, single-celled organisms living in the ocean, in hydrothermal vents, in volcanic soils, multiplying and dying and multiplying again with nothing more complex than themselves anywhere on the planet. And among those microbes, approximately 3.5 billion years ago, one lineage developed a capability that would change the chemistry of the planet more completely than any geological event since the Theia impact. They learned to photosynthesize. Photosynthesis, the ability to capture the energy of sunlight and use it to convert carbon dioxide and water into sugar and oxygen, is one of the most consequential chemical innovations in Earth's history. The sugar provides energy for the cell. The oxygen is waste. The cell exhales it into the surrounding water, the way a combustion engine exhausts carbon dioxide. Not deliberately, not usefully, just as the byproduct of a chemical process that happens to produce it. Each individual cyanobacterium, releasing each individual oxygen molecule, was performing an act no more conscious than the oxidation of iron in a piece of steel left in the rain. But there were trillions of these bacteria, and they had been releasing oxygen for over 1 billion years, and the Earth had a problem absorbing it all. The early ocean was saturated with dissolved iron from the volcanic sea floor, iron from the asteroid bombardment, iron in concentrations many orders of magnitude higher than in the modern ocean, and iron exposed to oxygen rusts. When the cyanobacteria began releasing oxygen into this iron-rich water, the oxygen reacted immediately with the dissolved iron to form iron oxide, rust which precipitated out of the water and sank to the seafloor. For more than 1 billion years, every molecule of oxygen produced by photosynthesis was absorbed by the iron in the ocean before it could accumulate in the atmosphere. We can read this history in the rock. The banded iron formations exposed in cliffs from the Pilbara in Australia, to the iron ranges of Minnesota and Michigan, to the Kaapvaal Craton of South Africa, are geological layers of alternating iron-rich and silica-rich rock. Each pair of layers represents roughly 10,000 years of oxygen production and iron absorption. These formations found on every continent contain locked within them more than 20 times the total amount of oxygen currently in Earth's atmosphere, all of it absorbed layer by layer over more than 1 billion years by an ocean filling itself with rust. The iron mining that built the American steel industry, the iron ranges of the upper Midwest, the massive open-pit mines of Minnesota and Michigan that supplied the steel, that built every bridge and skyscraper and railroad and automobile in the industrial era, is built on the accumulated rust of 1 billion years of bacterial breathing. You are embedded in the legacy of ancient photosynthesis. The infrastructure of American civilization was built from the oxygen waste products of organisms that died 3 billion years ago. Approximately 2.4 billion years ago, the ocean ran out of iron. The iron had been consumed, the banded iron formations had stopped accumulating, and the oxygen the cyanobacteria continued to produce as they had been producing it for 1 billion years, mindlessly, continuously, had nowhere to go except up, into the atmosphere. This event, the Great Oxidation Event, was the most consequential atmospheric transition in Earth's history, and it was simultaneously the largest mass extinction the planet had ever seen. Oxygen to the anaerobic organisms that had dominated Earth's ecosystems for nearly 2 billion years was a poison. These organisms had evolved in a world without oxygen, developed metabolic processes that were optimized for anaerobic conditions, and had no defense against the molecule the cyanobacteria were now releasing, in quantities that would gradually accumulate to 21% of the atmosphere. They died by the trillions. The Great Oxidation Event was caused by organisms that had no intention of causing it, who were simply doing what their chemistry required, whose waste product happened to be lethal to most of the other life on Earth. The organisms that invented photosynthesis triggered history's first mass extinction. But from that extinction came complexity. Oxygen-based metabolism is approximately 16 times more energetically efficient than the anaerobic chemistry that preceded it. More energy available per cell meant that more complex biological structures were thermodynamically feasible. Over the next 2 billion years, slowly with reversals and extinctions and stagnations that make the timeline look anything but linear, life accumulated complexity. The first eukaryotic cells with a nucleus, a far more organized and capable architecture than bacterial cells, appeared sometime between 2.1 and 1.8 billion years ago. Multicellular organisms followed, then animals with distinct tissues, then animals with nervous systems, then animals with eyes, and then approximately 540 million years ago, after 2 billion years of bacterial dominance and the slow accumulation of oxygen in the atmosphere, after the long Precambrian preparation, something happened in the fossil record that still astonishes paleontologists: the Cambrian explosion. In what the fossil record records as a geological instant, actually tens of millions of years, but effectively simultaneous on the scale of Earth's history, nearly every major animal body plan on Earth appeared: eyes, fins, shells, bilateral symmetry, predators and prey, nervous systems sophisticated enough to process information about the environment and generate directed behavior. The basic architectural templates that underlie every animal that has lived since. Vertebrates, arthropods, mollusks, echinoderms, all appearing within a single fossil layer. Not spontaneous generation, not magic. The result of 2 billion years of atmospheric preparation, finally reaching the oxygen threshold at which complex multicellular animal life became energetically possible. The result of 2 billion years of bacterial breathing that the bacteria themselves could not have imagined, had they been capable of imagining anything at all. Every breath you take is courtesy of an extinction event. Every animal that has ever lived, including you, is running on the oxygen waste of organisms that died trying to poison each other 3 billion years ago. The billion years no one counted. For 1 billion years, the surface of the Earth looked to any observer capable of observing it essentially the same: green-brown water under an orange-gray sky, bacterial mats on the shallow sea floor, hydrothermal vents releasing dark plumes of mineral-rich water into the deep ocean. Nothing moving, nothing hunting, nothing choosing. Across 1 billion years of bacterial life, the total behavioral repertoire of every organism on Earth could be summarized in 3 words: replicate, metabolize, die. And yet over that billion years of apparent stasis, the chemistry of the atmosphere was changing. Oxygen accumulating molecule by molecule, iron depositing on the seafloor layer by layer, the stage being set in a process too slow for any individual organism to experience, too long for any mind to hold in its entirety for everything that followed. There was no moment at which it became inevitable. There was no threshold that once crossed guaranteed the Cambrian explosion. There was only the slow accumulation of preconditions, year by year, century by century, millions of centuries, until one day the conditions were sufficient. And then life, as though it had been waiting for permission, filled every available space with complexity. The billion years of apparent stasis was not stasis. It was preparation. It just wasn't visible from inside it. The Cambrian had opened. Life had seized the sea. It would take another 100 million years for it to colonize the land, and another 100 million after that to fill the land with the density and variety of life we associate with the pre-extinction Earth. 300 million years of increasing complexity. Insects, ferns, reptiles, dinosaurs, flowering plants, birds, mammals, building toward an ecosystem that seemed, from the inside, permanent and self-sustaining and ancient beyond measure. And then, on an otherwise unremarkable morning, 66 million years ago, the sky opened. There was a morning 66 million years ago that was perfect. We do not know exactly where. Perhaps in what is now Montana, where the Hell Creek Formation preserves one of the richest records of late Cretaceous life. Perhaps somewhere in what is now India or China or North Africa, all of them warm, all of them lush, all of them saturated with the biological complexity that 150 million years of dinosaurian dominance had assembled. The geography was different. Then the continents were in different positions. The sea levels were higher, the climate was warmer than today. But the life was recognizable. Flowers had been recently invented, evolutionarily speaking. Flowering plants had appeared roughly 100 million years before this moment, and in 66 million years ago were already dominant. The fragrance of flowers was new in geological terms. The relationship between flowers and insects was new. The whole elaborate system of pollination and fruit and seed dispersal was geologically recent, a development of the past 100 million years, and on this morning it was everywhere. In the air, in the sound of bees that were in all essential respects the same as the bees you see today. Nothing in that morning indicated what was about to happen. An asteroid 10 kilometers in diameter, the length of Manhattan from the A financial district to roughly 60th Street, entered the atmosphere at approximately 70,000 kilometers per hour. The compression of air in front of it generated temperatures of 60,000 degrees Fahrenheit, hotter than the surface of the sun before the rock touched the ground. The impact in the shallow sea that covered what is now the Yucatan Peninsula was, in terms of immediate energy release, equivalent to approximately 10 billion nuclear weapons detonated simultaneously. In the first second, a column of superheated rock and plasma was blasted through the atmosphere and into space. In the first hour, material from the impact was raining down on every continent as red-hot ejecta. By the end of the first day, global wildfires had begun across multiple continents simultaneously, ignited by the thermal radiation from the re-entering debris. By the first week, a global cloud of dust and sulfate particles from the vaporized rock of both the impactor and the seafloor it struck, which happened to be rich in sulfur, had begun to spread across the stratosphere, reflecting sunlight back into space. Within months, global temperatures had dropped by estimates ranging from 15 to 26 degrees Celsius. Within a year, photosynthesis had effectively ceased across most of the Earth's surface. The food chains that depended on photosynthesis, which is to say all of them, began to collapse. Approximately 75% of all species on Earth went extinct. Every non-avian dinosaur, every species of large terrestrial animal above a certain body mass threshold. The marine food chains restructured catastrophically. 3/4 of everything died, and in the burrows. The small, nocturnal, warm-blooded mammals that had been scurrying in the undergrowth for the previous 150 million years. The creatures that had spent the entire age of dinosaurs hiding, keeping their body temperatures up in cold nights with metabolic heat, nursing their young living fast and staying small and staying hidden, emerged into a world that had no large predators. For 150 million years, mammals had been the footnote of Earth's story. They had existed since the late Triassic, contemporaneous with the first dinosaurs, and they had spent every one of those 150 million years in the ecological margins. Small, nocturnal, insectivorous, too small and too defenseless to compete with the saurian giants that dominated every terrestrial ecosystem. They survived by staying out of the way, by being small enough that they didn't matter, by hiding. In the ash and silence that followed the impact, they were the only complex terrestrial animals left in meaningful numbers. And the ecological space that had just opened the hundreds of niches, large and small herbivore and carnivore grassland and forest and river and coast, that 150 million years of dinosaurian occupancy had filled, was suddenly entirely catastrophically empty. The mammals moved into it. Not immediately ecologically speaking, the first few million years after the impact were brutal, as the surviving species competed for the reduced resources of a damaged world. But over the next 10 million years, the pattern was unmistakable. Mammals diversified explosively into every available ecological role. Small insectivores gave rise to large herbivores to carnivores, to aquatic species, to gliders to primates. The basic mammalian body plan, which had been constrained by competitive exclusion to small nocturnal insectivores for 150 million years, was suddenly free to explore every body size, every dietary strategy, every behavioral repertoire. Among the tree-dwelling lineages that emerged in this diversification, a group of small-bodied, large-eyed, forward-facing, visioned, grasping, handed mammals that had evolved in the forest canopy of the recovering Paleocene world. These organisms had binocular vision, precision grip, large brains relative to body size and intensely social behavior. They were the primates. They were, by the standards of the Cretaceous, nobody. They were small. They ate fruit. They lived in trees. They were the beginning of everything you are. The asteroid that killed the dinosaurs was not a disaster for the human story. It was the first chapter. Not A, but B. Not the extinction of the dinosaurs was a tragedy from which life eventually recovered, but the extinction of the dinosaurs was the specific, necessary precondition for mammalian diversification, and therefore for primates, and therefore for you. Remove the asteroid. The dinosaurs survive. The mammals remain in the ecological margins. The ecological space for primate evolution never opens. You do not exist. The worst day in the history of the Cretaceous was the first day of the Cenozoic, the era that produced every mammal alive today, including the one reading this. Over the 66 million years that followed the impact, the primate lineage diversified. The separation between the lineages that would become the great apes and those that would become other primates occurred roughly 30 million years ago. The split between the lineages that would become chimpanzees and bonobos and the lineage that would become humans occurred approximately 6 to 7 million years ago in Africa. The genus Homo, our genus, the genus characterized by bipedalism, dramatically expanded brain volume, and the use of stone tools appeared between 2 and 3 million years ago. And Homo sapiens, anatomically modern humans with the skeletal structure, the brain size, the facial architecture, and the behavioral capacity of the people living today, appeared somewhere between 300,000 and 315,000 years ago, based on the oldest known anatomically modern fossil specimens found in Morocco. 300,000 years ago. On the 12-hour clock of Earth's history, 19 seconds before midnight. In those 19 seconds, something happened that had never happened in the previous 11 hours. 59 minutes and 41 seconds of Earth's history. Something looked up at the sky and wondered where it came from. And then through a long, painful, frequently interrupted process of accumulating knowledge across generations, it began to find out. If you compress the entire history of the Earth, all 4,540 million years of it, into 12 hours on a clock starting at noon today, the timeline of everything we have been describing looks like this. Time on clock event. 12 o'clock noon. The solar nebula collapses. The sun ignites. 12:05 p.m. protoplanetary disk forms. Runaway accretion begins. 12:08 p.m. Earth reaches roughly its current mass. 12:10 p.m. Theia strikes the Earth. The moon forms. 12:25 p.m. First oceans form. Water delivered from the asteroid belt. 2:40 p.m. First living organisms, fossil stromatolites in the rock record. 7 p.m. Great oxidation event. Oxygen enters the atmosphere. 11 p.m. First multicellular animals. The Cambrian explosion begins. 11:23 p.m. Dinosaurs appear. 11:50 p.m. KPG impact. Non-avian dinosaurs extinct. 11:59:41 p.m. Homo sapiens appears. 11:59:59 p.m. tonight. Right now, you are reading this. 19 seconds. From the first anatomically modern human to tonight. From a small group of people in Africa using stone tools and ochre and fire, to a civilization that has sequenced the human genome, built the Large Hadron Collider, sent a spacecraft to Pluto, and retrieved the molecular building blocks of life from a 4.5 billion-year-old asteroid, 19 seconds on a 12-hour clock. Not 19 minutes, not 19 hours. 19 seconds. And for the 11 hours and 59 minutes and 41 seconds that preceded those 19 seconds, the universe assembled increasingly complex chemistry on this rock without any of it ever noticing what was happening, without any of it knowing it existed. For 11 hours and 59 minutes and 41 seconds, the Earth was a process without a witness. You are the witness. The atoms in your body, the specific carbon and nitrogen and oxygen and hydrogen and phosphorus and iron that are right now processing the meaning of these words, each one has a history that predates the sun. The iron in your blood was forged in the final seconds of a massive star's life, in a supernova explosion billions of years before the solar system existed. The carbon in your DNA was synthesized in the nuclear furnace of a star that died and scattered its ashes across interstellar space for millions of years before the molecular cloud that became the sun began to collapse. The oxygen you are breathing was exhaled by cyanobacteria in an ancient ocean 3 billion years ago and has been cycling through the biosphere ever since. The calcium in your bones was incorporated into the Earth during the late bombardment period, delivered in asteroids that formed in the outer solar system 4.5 billion years ago. Your atoms have been plasma. They have been stellar ash. They have been interstellar dust. They have been protoplanetary rock. They have been ocean water. They have been bacteria. They have been the body of a creature in the Cambrian Ocean whose descendants would, over 500 million years of evolution, eventually produce you. They have been present for and shaped by every major event in the history of this planet. And now they are arranged in precisely this configuration to ask, what am I? The universe spent 4.5 billion years building an arrangement of matter that could ask that question. And the question itself, your asking of it, every human being's asking of it, is not an accident. It is not a coincidence. It is not a footnote. It is what those 4.5 billion years were for. Not A but B. Not humans are a small species on a small planet in an unremarkable corner of an ordinary galaxy. And the fact of their existence is cosmically insignificant. But humans are the only known arrangement of matter in the universe that has succeeded. Through the long, improbable, catastrophe-laden process we have been describing in becoming conscious of the process that produced it. And that recursive awareness, that capacity to stand inside the story and know you are inside it, is not insignificant. It may be the most significant thing the universe has ever managed. We began this hour with a glass of water and a question, what am I? We have spent the hour tracing the chain of events that produced the hand holding the glass and the mind asking the question. What remains is not information. What remains is the weight of what we have learned pressing against the ordinary texture of a Tuesday morning. And there is only one place that weight belongs. You have been holding something for the past hour that you may not have named. It is not information. You have received information, yes, dates and mechanisms, and the names of ancient catastrophes. But information does not make your chest tight. Information does not produce the specific weight that has been accumulating since the sound of running water at the beginning of this hour. What you have been holding is something older than the information and more durable than any specific fact you have learned tonight. It is the growing recognition of something that was always true about your life and that you almost never let yourself fully feel. Your existence is not normal, Normal is a dead planet. Normal is a rock circling a star with no atmosphere, no water, no chemistry complex enough to self-replicate. Normal is what Mars became when its magnetic field failed. Normal is what every object in this solar system, except one, has been for the entirety of its history. Chemically interesting, geologically active in some cases, and completely permanently silent. You can look at the moon every night of your life, and it will never look back. You can stand on the surface of Venus, and no part of that world will register your presence. Across the entire observable universe, 2 trillion galaxies, hundreds of billions of stars per galaxy, an almost unimaginable number of planets orbiting those stars. The baseline condition is inert matter moving through space according to the laws of physics, doing nothing that could be described as noticing. And then there is this planet. And then there is you. Think about what it took. Not abstractly, concretely. Think about the chain we have traced tonight. A star had to die and scatter its ashes across interstellar space. A supernova shockwave had to compress those ashes at exactly the right moment. The resulting disk had to be positioned at exactly the right distance from the right kind of star. 200 million years of bombardment had to generate enough heat to melt the iron to the core. A planet moving at 9 kilometers per second had to arrive at exactly the right angle to deliver exactly the right tilt. Jupiter's gravity had to be exactly the right strength to disturb exactly the right asteroids into Earth-crossing orbits. The iron in the early ocean had to absorb 1 billion years of bacterial oxygen, slowly enough not to kill everything before complexity became possible. An asteroid had to arrive 66 million years ago at exactly the right angle to cause exactly the kind of extinction that opened the ecological space for mammalian diversification. Every single one of your ancestors back to the first self-replicating molecule in an ancient tidal pool had to survive long enough to reproduce. Not most of them, every single one, in an unbroken line across 4 billion years. Remove any one condition, change any one variable. The story ends before you begin. The philosopher Albert Camus wrote that the only serious philosophical question is whether life is worth living. He was wrong about the question. The question is not whether life is worth living. The question is whether you have actually been noticing that you are living, or whether you have been moving through your days too quickly to register that each one of them, in the full accounting of what it cost to produce, is a gift so improbable that no theology has ever adequately described it. Think about yesterday, not the dramatic moments, not the high points or the difficulties. Think about the ordinary texture of it, the weight of the coffee cup in your hand in the morning, the specific angle of the light through the window at 7 o'clock, the sound of the house waking up around you, the unremarkable middle part of an afternoon that you moved through without fully arriving in it, because you were already mentally somewhere else. That afternoon was resting on a foundation of fire. It was held up by the death of a star that burned out before the sun existed. It was made possible by 200 million years of planetary bombardment that happened to generate the iron core that generated the magnetic field, that preserved the atmosphere that you were not conscious of breathing. It was shaped by a collision 4.5 billion years ago that tilted the axis and gave the seasons their meaning. It was watered by asteroids. It was aired by bacteria. It was handed to you by an extinction that cleared the board for mammals and primates and, eventually, for whoever was sleeping down the hall that morning in the house you have been moving through too quickly to actually inhabit. We almost sleep through it, all of us, every day. Not everything, not always. You cannot sustain the full weight of 4 billion years pressed against every passing moment. It would not be livable, and it is not the point. But sometimes in the gaps between urgency and routine, when the world goes quiet for a second and you find yourself simply present in it, let yourself feel it. The full improbability, the full weight of what it required. The iron in your blood was forged in a dying star. The oxygen in your lungs was exhaled by bacteria that lived 3 billion years ago. The water you drank this morning was delivered to this planet by asteroids that formed before the sun. The seasons that have organized every year of your life were created by a collision that destroyed the world entirely and replaced it with something better. You are the universe's most improbable accident, and you are the only accident the universe has ever produced that knows it is an accident. This is what the science actually says in the end. Not that we are small in a vast and indifferent universe. Not that the cosmos does not care about us, it doesn't. But that framing misses the point. The point is not that the universe cares. The point is that from within a universe that does not care, something assembled itself, through fire and collision and patience and catastrophic luck, into an arrangement of matter that cares enormously. That feels the weight of 4 billion years in an ordinary morning. That can be undone in a moment of genuine attention by the specific improbability of still being here. The universe spent 4.5 billion years building the conditions for this recognition. You get to do the recognizing. That is what you are for. We are not the purpose of the universe. We are the moment the universe first noticed itself and decided that was enough.